Okay. Hello, everyone. As you know, this is the second module, second part. We'll talk about PIC instructions in assembly language programming. As you know, after this, everybody will go into their own groups. One group will go into assembly, basic, and so on, and C, for example. And you will learn how to simulate a program. Okay. All right. Now here we will talk about, or this section talks about PIC microcontroller instructions. And as you all know, every microcontroller has a built-in instruction set. And then this document talks about what do we mean by hex extensions and so on. That's why we have studied in the previous section hexadecimal versus binary and conversions and so on. And let's see. Well, this one talks about a mnemonic. What is a mnemonic? It's a combination of letters that suggest the instruction's purpose. And this next is a very good instruction. For example, if the instruction code is hex 2800, you wouldn't know what it means. But if it says go to, you would actually understand what the instruction is supposed to do. Now in PIC, we will only have 35 instructions, and when you want to write the program or code in assembly language, as you know, you must follow the rules, and here are the extensions that you should be familiar with. .asm file, this is your source file, and it is what you create that starts the whole thing rolling. And again, after this module, you will be able to actually work with all the .asm, .hex, and list files, so, for example. And .hex file, this is what you will download to the PIC. And again, you will be able to try this in the next laboratory session. And the .list file, that's a combination of the ASM and the hex files, and this will contain the line numbers, and especially when you have errors, it is easier to go and find the error, where your error is, in which line. Okay, this talks about the assembly language format, and again, I'm not going to spend too much time on it because the MPLAB IDE and PIC2, you will be using these in the lab. And here is the general format for an assembly instruction. The first column is your label column, and you don't have to have it, but for some instructions, for example, when you have go to, or if you want something that to make sense to you, or you will be using that label, that will be your first column. Then the second column is the operation or opcode column, or you may have an assembler directive, which we will talk about what an assembler directive is in a few minutes. And then next column is the operand column. This may contain a label. For example, you may have something go to main or something like that. So that may have that column may have a label, an expression, or a combination of symbols and expressions that may separated by commas. And finally, the fourth column is your comment. column. If you pay attention, there it has a semicolon. So the compiler will ignore anything after a semicolon on that line, and it's a very good. Actually, it's recommended that you write comments in almost every line if you can, or so that somebody else can follow your program, or if it has been some time that you have written the program, if you wanted to go back, you can take a look at the comment line. And here are the assembler directives, for some of the assembler directives. For example, the EQU, that's a variable definition. Later on, you will see some examples. ORG is the starting address assignment. For example, before a data, you start your data, or before the program, you have an ORG assembler directive. And DT is for data table assignment. Now, general instruction set types, complex instruction set, computer versus RISC, sys versus RISC. We've already covered that, I believe, in the very first module. So I'm not going to go over it that much. I will only say that here for CISC, each instruction takes several clock cycles to execute, and however, RISC, this is fewer, simpler, less sophisticated instructions, much faster execution, and most RISC instructions execute in a single clock cycle. Here is a list of 35 PIC instructions. I would recommend that you print this page and make it available next to you so that you can refer to it. Very quickly, we are going to be going over each instruction, what it means, give you an example, and what kind of status is affected will also be given. As you can see, many of these instructions takes one clock cycle, but some of them takes 2 clock cycles, and it depends on if it is true or if that instruction is true or not. And here it is, here they are, and also the return instructions and so on, and they will take 2 clock cycles. Okay, in this list, in the previous list, as you can see, you see F, comma, D, or K, or whatever, all these things, and here is the explanation. F stands for the register file, whatever that file is. D is the destination, and if D is 1, it means that the final value will be in that register, or if D is equal to 0, the final value after the execution will be in W register. K stands for the literal. The first instruction is add literal with W. It adds the contents of W register to the contents of the selected register. And here are 2 examples. Here it is, and this is, for example, a W before the execution. This is after the execution, and it adds the content. And as you can see, the status bits are affected is given right here. The next instruction, add W and F. Add contents of W register to the contents of selected register. Result will be in W or F. As you can see, I highlighted these because this is comma 1, the destination. The final addition, the value will be in the in this register, which is here. But if it is comma 0, the final value after the addition will be in the W register. As you can see, this instruction, for example, on example 2, adds the contents, whatever is in temporal register, to the contents of W. Here it is, and because it is comma 0, the original contents of temp will not change, but the original contents of W will change, and it will get the new result. Third instruction is AND LW, AND literal with W, and contents of W register with literal contained in instruction. The result will stay in W. Here the literal is 0F, so that's actually your data. So what's happening is here you will take the part of the instruction, which is your data, 0F, your literal, and that will be added to the contents of W. The result is in W here, and here you can see that. The next instruction, AND W with F, and the contents of W register with contents of selector register, and then the result again, if it is 1, if it's comma 1, the result stays in the goes into the register here, FSR. As you can see, FSR value changes because this is the answer. Here this is comma 0, the result goes into the W register. BCF, bit clear F, this clears selected bit in selected register to 0. It says BCF status comma Z. It means that the Z bit of the status register is clears. So if it was 6.5 in hex, it becomes 6.1. In this example, temporary register, which originally it is 7.7 hex, bit 0 is clears or clears, so it becomes 7x. Next one is bit set F, set the selected bit in selected register to 1. This instruction means that the bit 2 of status register will be set. And you can try it yourself and see if that is the case. Here, the temporary register's bit 0 is set. Originally, bit 0 was 0. It becomes 1. This instruction is bit test F, skip F, clear. Now, it tests specified bit in selected register. Skip the next instruction if bit tested is clear or 0. So here, this is the instruction. It said the second bit of the status, which is Z bit, is tested. If Z is equal to 0, because it skips if clear, if it skips this instruction and goes to the main. Otherwise, if it is not clear, if it is equal to 1, it goes to the next instruction in line to be executed will be go to loop. Here, temporary registers bit 7 is tested, and if it is equal to 0, it goes over this instruction. It doesn't execute the go to, but if it is equal to 1, it executes go to. It does not skip. This one is bit test F, skip if set. So this one skips if it is set, just like the previous one, but it skips only if it is set. And here is the answers. Because it is set, it skips. This instruction is the call instruction, call subroutine. For example, this one says call search. When this call happens, then the return address, remember, if the program counter is pointing to call, then the next instruction in line, which is PC plus 1, will be your return address. That will be saved and pushed onto the stack so that program counter will get the address, whatever the search's address is, the beginning address of that labeled search is. So call is an 11-bit instruction, and it can only range between 000 through 7FF. Clear F instructions clear selected register to 0. For example, when this says clear F counter, if the counter has some value after the execution, it clears, and obviously it also sets the affected bit. Next instruction, clear W. It just clears the W register, as you can see here. This one, clear watchdog timer, this instruction will be explained more in later in, I think, I believe module 5 or in one of those modules. So here's the instruction. If you want to take a look at it at that time, you can come back and take a look at it. This instruction clears the watchdog timer. It resets to the 0, and also resets these bits. Complement F, complement selected registers contents, the ones become zeros becomes ones, and the result stays in W or F depending on if it is one, destination is 1 or 0. If it is 1, then the flag, the result is in flag, otherwise it's in W. Decrement F. Decrement the selected register. Now, again, result in W or F, just like the previous one. Assume that flag is initially was 0, 1. When you decrement that, it becomes 0, but because this is comma 0, flag doesn't change, but the result goes into the W register. Here, temporal register original was FF, decrementing is FE. Because it is comma 1, temporal register itself was decremented. Decrement F, skip of 0. Now, decrement is specified register, skip next instruction if register contents is equal to 0. Here, it says decrement F, decrement this counter, so assume that the counter is 6A. It is decremented to 6-9, and the result is in 6-9 because it is comma 1. Here, decrement counter, counter 0, counter comma 0. So you expect that the result to be in W, and if the counter is 0, 1, and then it becomes 0. Counter, as you can see, counter contents do not change. Because this is 0, then the program counter, it is incremented by 1, which means that it skips the next instruction. Go to, this is an unconditional branch. Here, for example, go to route. So there you don't, because it's an unconditional branch, the return address do not go to stack, because you're not going to come back unless there's an instruction. The unconditional branch, again, it's not like call. So the program counter just is loaded with the address of the route. So go to is an 11-bit instruction, and it can only range between 000 and 7FF. Increment F, increment the selected register, and here it is. Depending on comma 0, the destination is in W register. If it's comma 1, the result will be in the temporal register. Here, it results is in W register. Increment F, skip of 0. Increment specify register, skip next instruction if register contents is equal to 0. So here, assume that counter was FF, and when you decrement that, it becomes 0, 0, and it stays in counter because it was comma 1. And because it is 0, 0, you skip an instruction, so program counter gets address plus 1. Here, the counter the increment instruction comma 0, so the result will be in W, and because it is not 0, then program counter gets the next address in line. It does not skip. Inclusive OR, literal with W is the next instruction, or the contents of W register with literal K contain an instruction, and result will be in W. Here are the two examples. This is inclusive OR W with F. Is similar, but depending on the destination, comma 1 or comma 0, the result will be in either in a register or W. Move contents of F into W or F. Move a copy of selected register's contents into W or F. Here are some examples here. Move literal to W. So just load W register with this literal, which is a part of the instruction. You can see it here. Move W to F. Move a copy of W register's contents into the selected register. So if W is AA, after the execution, temporal register will get AA, as you can see from there. This is a no operation, do nothing for one instruction cycle. It just uses up clock cycle. Usually you use that when you are writing loops, timing loops. You may need to use a number of these no operations. Return from interrupt. W register is unaffected and interrupt flag bit is cleared. Here, usually, the program counter is address of the interrupt service routine, has the address of interrupt service routine. Now, when you have a return from interrupt, program counter gets the top of stack content, which was your return address when you saved it before you jumped onto the interrupt service routine, and GIE bit is set to 1. And this is a 14-bit instruction, and it will return back to wherever it was called. Return and place literal with in W. So this one you return and whatever the W and the W return from subroutine and load W register with literal. So here is an example here that you can see. Return from subroutine. Again, the W register and interrupt flag bits are unaffected. It just goes and takes the top of the stack content, which was your return address, and goes back to wherever the program was originally before it came to that subroutine. Rotate left F through carry. Here are, you can just, very nice examples here. This is the, assume that FSR has this value and you're rotating to the left. So in that case, this one goes here and the FSR gets this value. But because this is comma 0 and W gets the final value after the rotation. Rotate right F through carry. Is a similar example. You can follow it very easily. Here, this is 0, so comma 0 results goes to W, comma 1 result is in the register. Sleep, enter sleep mode, shut down the microcomputer core or instruction oscillator to reduce power consumption. Wake up by a reset watchdog timer or an external interrupt. And this gives you the values to be set or reset. Subtract W from literal, subtract contents of W register from the contents of selected register by 2's complement arithmetic and result in W. Here are actually 4 examples, and I recommend that you go over them and try to be able to follow it. Subtract W from F. Subtract contents of W register from the contents of selected register by 2's complement arithmetic, result in W or F. As you can see, I've highlighted them. These are comma 1, result stays in the register. These are in stay comma 0. The result stays in or goes into W register. Swap, exchange the upper and lower nibbles, 4 bits of the selected register. And here, for example, this is swap F counter comma 0. So if the counter is 6C, and then after the swap, the result goes into the W register, and then here is the result. C6 is swapped, and the counter or it stays the same. Exclusive OR, literal with W, exclusive OR contents of W register with literal, which is a part of the instruction and result in W. Here are, you can see the exclusive OR examples. And finally, exclusive OR W with F, exclusive OR contents with W register with the contents of selected register, result stays in W or F depending on 1 or 0 here. All right, these were the 35 instructions, and you can always go back and take a look at them. Here, graphic representation of the maps are given. The only thing that we will be using throughout the modules is PIC16, F84A, and the others are given also. But these, I recommend that you make a copy of this, make it available for you to follow. This gives you the addresses of the port A, port B, trace A, trace B, which we will talk about in other modules throughout these modules. And all of these you will be referring back to both in Bank 0 and Bank 1. And the others are also given just for your information. Here, 84A block diagram is given. We have already covered this in detail in earlier modules. Here are more maps. This is 88 block diagram. 77A. Actually, you may have 77A chip, so if you want to program that, you can refer to this map. Here is the block diagram of 77A. Now, here's some information about setting and clearing bits. There are 2 methods in which bits can be set or cleared using PIC microcontroller. The first is by using bit set and bit clear instructions, which we've seen before. For example, this is clear bit 7 of register 20 in hexadecimal. This is set the carry flag, and this is the clear bit 6 of the that register. Now, the second way is to set or clear bits using logical instructions, and that way any number of bits you can set or reset. In the previous one, you will do these bit at a time. But if you want to set or reset a number of them, then you can use these instructions. For example, in the first one, bits 0, 5, and 6 are set. Here you clear the bits 4 through 7 and so on, and take a look at these. Actually, I recommend for you to go over the second lab, and you can try each of these instructions and simulate them and see what happens, and feel and understand them in more detail. Logic and math operations. There are actually the simulation lab. You will be using these instructions. Then you will be writing a program where you need to write a code that implements in instructions like this. For example, here, if you wanted to add AB 69, here is the answer, binary addition. So here, what you are doing is you're loading W with 69 and adding to AB, and then the result will going to register 1. Another addition example, you're loading W with 4C, adding it to 3E, the result will go into register 2. Subtraction example, as you know, if you do the subtraction by hand, you take the bottom number, take the 2's complement of that and add them together. But if you write the assembly code, you load the W with 69 and subtract from AB, and the final the result will go into register 3. Okay, here's another example. And this is again, we've covered this before. As you can see, when you are writing an instruction, you use the label, opcode, operand, and comment. We've gone through these. There are these things you can just go ahead and use them, read them if you are not too familiar with it. But let's talk about some of the addressing modes. Here, indirect addressing mode is actually, let's start with literal, or this is the immediate, then direct and indirect. Now, indirect addressing mode is especially well suited working with arrays. And here's an example, very nice example that you can follow in indirect addressing mode. Inherent mode, the operation within opcode, within the opcode, no operand needed. For example, no operation, clear W, sleep. You don't need anything else. So these are called the inherent addressing. Immediate addressing, the operation directly involves fixed data, and the data or literal is part of the instruction. So you don't have to go to memory to get the data. That's the immediate addressing. But indirect addressing, operation involves data in the memory, so you have the address and you have to go to that address to get your data. And please go ahead and follow these small programs. And again, I recommend that you simulate them to see and run them each instruction at a time to see what's happening to each register or each address after the execution of each instruction. And again, as you can see, these are you write the instructions like this, and these are the comments. I think it helps if you write the comments. Relative addressing mode operation involves relationship of current program counter, and here are some examples. And index mode or indirect mode, here FSR holds the address as a pointer. INDEF, an actual physical register, is the data pipeline. And please go ahead and try to follow these examples before, if you have time, before the lab session. Here are nice, here's another index mode example for you to follow, even another one. And there are some student assessments and some homework for you to do, or for your students to do. Thank you very much for listening.